Okay, N-type thermistors. We've mentioned these briefly before. This is the symbol, and this is a typical resistance temperature characteristic. So as the temperature increases, the resistance decreases. This would be for an N-type thermistor, which is what we normally mean at A-level when we talk about thermistors. There are P-type thermistors, which is a positive temperature coefficient, but generally speaking we refer to N-type. So this is used a lot in temperature and heating control systems. So it's made from a semiconductor, and if we increase the temperature, then we release some of these electrons which were previously trapped in a valence band, and we can move those into the conduction band. So what we're saying is, as the temperature increases, the number of free electrons increases. Therefore, for the same voltage, R equals V over I, we have a larger current, therefore the resistance goes down. LDRs are light-dependent resistors. This is our symbol, with or without the circle, that's optional. The basic shape is very similar. So as, in this case, the light intensity increases, the resistance goes down. So once again, it's a negative exponential relationship. It's also made of a semiconductor, not a siliconductor. It's made of silicon, which is a semiconductor. And the principle is similar to what we saw previously with the thermistor. So as the number of photons increases, because the light intensity increases, then more electrons are released from the previously trapped valence band, and we increase the number of delocalized electrons available. So the basic principle is very, very similar. Okay, so let's have a look at this worked example. So we have a fixed resistor, 12 kilo, we have an LDR, and we have a supply voltage of 9. So we're trying to find what is the potential difference across the LDR when we're in the dark. So we have a high resistance of the LDR, and it's of 6 mega ohms. So we can use our new formula. So the voltage across the LDR is equal to the supply volts, Vs, multiplied by the resistance of the LDR, divided by the total resistance. So we have 6 mega divided by 12 kilo plus 6 mega, and that's going to equal 8.98. So that shouldn't surprise us, because in the dark we have a high resistance, therefore most of the 9 volts, 8.98, is taken by the LDR. However, if we increase the light intensity and we reduce the resistance of the LDR to 1 kilo, then we can change 6 mega to 1 kilo. We can do the calculation again and we get 0.69. Again, that shouldn't surprise us. As the light intensity increases, the resistance of the LDR has decreased substantially. Therefore, the voltage that it will take of the 9 volts is reduced. And this idea of changing the voltage output, or the voltage across a particular component, as the resistance varies due to the conditions, is the fundamental principle behind potential divider circuits. Okay, let's look at a practical circuit. So I've got a series circuit, I've got my LDR, in this case without the circle, in series with a fixed resistor. How will we connect a night light, so a bulb, into this circuit so the bulb comes on when it gets dark? Okay, so we'd have to connect the bulb in parallel across the LDR. So why is that? So this would be our typical 3 or 4 mark answer if this was an exam question. So first of all, we need to say that as it gets dark, so as the light intensity drops, the resistance of the LDR increases. According to the potential divider formula, or our understanding of voltage in a series circuit, if the resistance of this section here increases, or the LDR increases, it will then take a larger share of the total volts. And because the bulb is connected in parallel, then they have the same voltage across each component. Therefore, the bulb will now turn on because the voltage across it is sufficient in order for the bulb to light. So that's our basic principle. So we're changing the distribution of the voltage depending on this variable resistance. Now, we could put a little caveat here. In actual fact, if this were a real circuit, a practical circuit, you might have some kind of additional amplification, so maybe a transistor or something else which is beyond the scope of physics A level. But the basic principle is as shown here.